All right, I'm gonna start talking. If you still need some time to write, that's totally fine. I'm gonna be adding a little bit to the page just so that we can kind of talk through some specific bits. So what this top part is, this is like our technical definition of this intermediate value theorem, which is something that'll be used, again, like for the rest of your math career. You have been using this, it's just we've not put it in these formal terms really before. What this is saying is that if I have two x values, I'm given a and b, and I know they don't have the same y value, they don't have that same answer. Since we're in polynomials, we are in continuous functions. There are no asymptotes, we don't have any discontinuities, nothing. We are on a continuous function. I'm going to put a little sketch up here real quick. What that means is since I know I have an x value that gives me a y value, and an x value that gives me a y value, I'm going to hit every x value in between a and b, and I'm going to hit every y value in between f of a and f of b. I'm not missing anything. There's no discontinuities in there. So I'm hitting every value between a and b, and I'm hitting every value between f of a and f of b. So it's very generic and very kind of, why the heck do we even care? We use it like this. Because if I have a function, and I know a and b, and I know their values, and let's say f of a is a negative number. So my f of a maybe is less than 0. And I know b. And I know b is probably a positive. F of b is a positive number. So if f of b is greater than 0, I know somewhere in between a and b, I have to have a root. If I have a positive value at b and a negative value at a, somewhere in between these two values, I have a root, a solution, a 0 or x-intercept. I don't necessarily know where it is. Like it could be that this is going like this. Maybe it's going over here like that. But if I know these 2 points, I know that somewhere in between there has to be at least one root. Maybe there's more. Maybe there's not. But somewhere in between there, I have to have a root or I have to have a 0. So this is how we're going to use it. We're going to be given like an equation and an a and a b. And we're going to be asked to prove or solve to see if there is a root between those two values. So what we're trying to do is we're trying to see if one of them has a negative y value and one of them has a positive y value. If one of them is negative and one of them is positive, I can guarantee there has to be a root between them. If they have the same sign, we can't tell. They might not. So we're going to try working with problems like this. This is definitely our wordiest thing of the day, especially like definition-wise. It's the only thing we have. And so we're going to be given an equation. We're going to be given an a value. We're going to be given a b value. And we need to try and prove or see if there is a root between them. Does anyone need more time on this page? Looks like most of the pencils have slowed. Okay. This is how we tend to get these problems. And there is at least one, I think there's 2 on the homework, 2 or 3. So we're going to be using the intermediate value theorem. Basically means we're going to do some substitution to show or prove that f has a 0 between a and b. So we're given f of x as x cubed minus 4x squared plus 3x minus 2. And we are given our a and our b. We are given a of 3 and we're given b of 4. So what we need in order to use that intermediate value theorem is I need to know what the value of f of a is. So we're going to substitute it in. We're going to take our a, which is 3, and substitute that in. So that's going to be what happens when we get 3 cubed minus 4 times 3 squared plus 3 times 3 minus 2. And we're going to simplify that as much as we can, as far as we can. We can do this by hand. We can do this on the calculator. We have tools. We're going to use them as much as we can. So simplify this. And go for it. What are we going to get for our value of f of a? Or what do we have as the next step? Yeah, it is going to wind up being a negative 2. We wind up with, if you're going to do it by hand, we wind up with our 27 minus 4 times 9 gives us 36 plus 9 minus 2. So f of a equals negative 2. So I know that my f of a value is less than 0. It is a negative number. This is our first piece that we need. Then we also need to know what f of b is. Round 2, fight. So we're going to find f of b. That's our next piece. F of b. Same vibe. We're still doing that same kind of substitution. Except this time we're substituting in that 4. We're going to have our 4 cubed. Minus 4 times 4 cubed squared. Is 3 times 4 minus 2. And again, we're going to simplify it as much as we can. Again, we can do it by hand or we can do it in the calculator. We're going to have our 64 minus 64 plus 12 minus 2. What do we get? What is our value for f of b? So our f of b is 10. So now I know my f of a is negative 2. My f of b is positive 10. Since I have opposite signs on there, I know for sure this is a negative value. I know for sure this is a positive value. What that tells me by my intermediate value theorem is somewhere between these, we have to have a 0. We have to have a root. I cannot get from negative 2 up to positive 10 without going through 0 somewhere. I have to hit 0 somewhere in between there. So we are going to have to write a dun-dun-dun sentence. I know, we're Englishing in the math class. It's horrifying. Ew. All right, so the way we're going to write it is we're going to say, since our f of a is less than 0, meaning it's negative, and f of b is greater than 0, positive, there must, or has to, or is guaranteed, wording is irrelevant. I don't care what words we use, just giving the same information. There must be a root, 0, x-intercept, solution, you know, all those synonyms. There must be a 0 in the interval. I know, it's a full sentence, ew. Between 3 and 4. If you put it with brackets, it's not wrong, but we already know it's not going to be at 3 because at 3 we're at negative 2. I already know it's not going to be at 4 because the value at 4 is 10. So it's not going to be on 3, it's not going to be on 4. So it's not wrong to have the brackets, but I can be more specific in saying it's got to be less than or more than 3, but less than 4. Somewhere in there we have a 0, we have a root, we have a solution. So it's one of those things that we've logicked our way through before, but this is the like formal mathy rules for it. Okay. We're going to do another one like it, but questions on this first one? I say it's one of those things that sounds super complicated. Plug and chug. As long as one's positive, one's negative, we're good to go. There's a 0. If we do not get different signs, that means there might be a 0, there might not be a 0, and we don't have any way of confirming it. Okay. Let's do another one. Sometimes they like to be neat and give us fractions. Luckily, we get to use calculators. Isn't that nice? We didn't used to be able to. They had to do these all by hand. Yeah. Like 3 years ago, they didn't get to use calculators at all. Gross. So we're doing the same kind of thing. We've got our f of x here as our 2x to the 4th plus 3x minus 2. And this time they've taken our interval and they've made it even closer, made it even smaller. And a lot of times that's what we'll wind up doing with the intermediate value theorem if we use it for solving stuff, is because we're like, well, I can prove it's here, so I'm just going to shrink it and shrink it and shrink it. I'm trying to figure out where those roots are. That is a lot of what one of the calculus courses, isn't it? Having a hard time remembering which one is finding roots when they're decimally and gross and it's polynomials. So we're going to do that same kind of thing. We're going to find our f of a, we're going to find our f of b, and if it works, we're going to write our whole dang on sentence. So we're going to substitute this in, and this is going to be another one of those times it's probably going to be really helpful to use a calculator, especially on these yellow calculators that'll keep our fractions as fractions. If you write things as decimals, as long as you don't have to round, you can use a decimal. However, once you get to the point that your decimal is too long for the calculator or you have to round it somewhere, not good anymore. Rounding changes your answer. Do not round decimals. If you have to round your decimals, switch it back to a fraction. We are keeping our answers as accurate as possible. Fractions, awesome. Decimals, fine, as long as we haven't rounded them. If you round them, you've changed the answer. It's wrong. So do not round off your decimals. I'm fine with you using them. Do not round. Do not round. Do not round. So things like thirds you don't want to have as decimals because you'll run out of paper in the world. So we're going to simplify this, get our f of a all the way down. Again, you can do it by hand or you can do it in the calculator. Second column, third button down is our fraction button that looks like a fraction. Love that button. Favorite button. What do we get when we simplify our f of a? Negative 3/8. So if you're typing it in the calculator, make sure you're being real careful. Get your fractions in the right spot. You can put the fractions in parentheses with powers on the outside. Totally fine. The calculator can do it. Awesome sauce. We are going to do the same thing for our f of b. You can absolutely do these by hand, but they are not pleasant. They're doable. Definitely doable. They're just not very pleasant. So we're going to put our 3/4 in on this one. You will probably have a quite large denominator. If your denominator is 3 digits, you are fine. This would be one of them where our decimal gets too long. And it will wind up running off the screen.
113 over 128.
Yeah, our fully simplified fraction is going to wind up being 113 over 128, which is decimally and gross and about 0.883 with rounding. We don't want to round. But it goes all the way past the edge of the calculator, so we need to put this back as a fraction anyway. If you're in the calculator and you have things as decimals and you want to switch it back to be a fraction, or the other way around, you want to switch your fraction to a decimal to see it, right above the enter key are these two triangles. Looks like a play button and a backwards play button. If you hit that, that's the switch to fraction mode and switch back to decimal mode, and it'll just keep flipping it back and forth. So that button with the two arrows will switch you between fractions and decimals. So the whole point with these intermediate value theorem problems is we're going to do some substitution, and then we're going to look at our two answers here. Do we know for a fact that there is a root between 1/2 and 3/4?
Yeah.
We do. Because my f of a, my f of 1/2 is a negative number. My f of b, my f of 3/4 is a positive number. This is positive. Not very big, less than 1. But it's positive. Since I have a negative value and a positive value, I have to hit 0 somewhere in between. To get from negatives to positives, I must go through 0. So this one definitely does work, and we can write our sentence again. Yay. Since f of a is let's see, my a is less than 1. Since f of a is less than 0, and f of b is greater than 0, there is a root in the interval. You don't necessarily have to write the word interval as long as you remember that, between 1/2 and 3/4. It does have a tendency to look like a point. It's not the point, it is the interval between 1/2 and 3/4. So if we look at this and we think point and we go, oh wait, I have to remember it's an interval, write the interval. Write the word the interval. If you're like, oh, that makes sense, it's an interval, you don't have to write the word interval. Trying to make sure we keep track of that.
Between.
That works. In between, betwixt, feeling Shakespearean. Within, synonym away. As long as it makes like sense as a sentence, I don't care what specific words you choose. English is weird. Spelling is a suggestion. As long as I can figure out what you meant, we're cool. If I can't figure out what it is, if I have to Google, or like if I have to voice to text your word and be like, what does this word say? Then it's probably a problem. I get it, because I occasionally have to voice to text a word because I can't figure out how to spell it bad enough that even Google doesn't know what I mean. Happened yesterday. I don't even remember what word it was, but it happened yesterday. Oh, it was bureaucracy. I couldn't even get close enough for Google. I had to voice to text it. Spelling is a suggestion. Okay? If it's close enough to get your point across, close enough for me. Questions on these ones? Okay. The next kind of problem we're going to run into in 4.1 is based off a lot of the stuff we did yesterday, tucking in one more thing from last chapter that they want us to kind of use in here, kind of help being a structure. And that's going to be given a problem, given an equation, that we are asked to sketch it. We're also asked to figure out the intervals where it's above 0 or below 0. When it has this piece, our f of x greater than 0, f of x less than 0, that means they want us to think about a positivity table, which is when we did last chapter with our inequalities, where we do our little number line thing, and we put our roots and our factors, and we figure out whether it's positive or negative, that kind of guy. So we're going to do one of those with these so we can see what they're intending us to do. I know a lot of times when we're doing these sketches, we can kind of intuit our way past instead of doing that positivity table, but like we're going to do it. So we're given this equation here. Our f of x equals x cubed minus 3x squared minus 10x. First thing we want to do, from this bit here, we can get the information we looked at yesterday. What is the degree of this equation? 3. It's our largest exponent. What is our leading coefficient? 1. It takes me longer to write leading coefficient than it does. There we go. Think of it. I usually abbreviate that, so I'll put D for degree and LC for leading coefficient. Just since it's the first time today, I'm writing the words out. From that and that alone, I can get my end behavior. Because for end behavior, are we thinking about evens or odds? Odd. And then are we going to be thinking positive or negative? Positive. Our leading coefficient is positive, positive 1. Our degree is 3, which is an odd number. So from that, we can do our end behavior, because I know that my right arrow, as x approaches positive infinity, it's going to have that same sign as my leading coefficient. My y is going to go towards that positive infinity. If it helps you, you can put the little plus sign right there. It's matching the sign of our leading coefficient. The evenness or oddness tells us what's going to happen with our left arrow. So with our odd functions, is x going to approach negative infinity with y going the same or opposite? Opposite. Odds go in opposite direction. Remember, odd ducks go to the disco. Odd degreed functions will go in opposite directions because odd ducks go to the disco. So our y will approach negative infinity here. So when we're trying to make a sketch of this, with that information alone, I know a little bit. I know my right arrow is going to point up, and I know my left arrow is going to point down. But at that point, that's about all we got. What else do we need to know in order to make a half-decent sketch? Yep, we'll need to know when it's greater than 0, when it's less than 0, so we know when it's above or below. What might help us find that out? Roots. I'd really like to know where it's crossing this line. I want to know when it is 0. How can I find roots from something like this? There's a GCF of x. Oh, snap, we're going to have to do a little bit of factoring. What? So we have a GCF of x here. I can for sure rewrite this as my x times x squared minus 3x minus 10. Means the same thing. That gives me a little bit of information. Can I do more? Factor. That's a quadratic. We can factor this sucker. We need a pair of numbers that multiplies to make negative 10, adds to make negative 3. What are our numbers going to be? Because our pair of numbers that multiplies to make negative 10, adds to be negative 3 is going to be a negative 5 and a positive 2. So we're going to have our x with our minus 5 and our x with a positive 2. So what are our roots or our zeros, x-intercepts? 0. Same again because they overlapped and I didn't hear signs. 5 and negative 2. I know a lot of them were said, but it just was just all smushed. So negative 5, 2, all overlapping. So I know where my roots are. We're going to have a root at 0. We're going to have a root at negative 2. And we're going to have a root at 5. Sketches, we're not going to have to go super duper specific on where they are. We don't need to count out numbers, any of that jazz. Getting the vibe. And we could logic our way into a half-decent sketch here. I'm going to show us how we prove it, not just brute force logicking, even though I know we can. I know we can. I'm still going to give us the tool that the book wants us to use to figure out our greater than, less than situation. We used these last chapter when we were talking about inequalities, and we would take our roots and we were putting them on a number line, smallest to biggest. So we'd have our -2, then 0, then 5. And we put all of our factors in a column down the left where we'd have our x and our x minus 5 and our x plus 2. Like this. And we want to know when our function combined together, positive versus negative. So we're going to look at each of our factors. We're going to look at each of these chunks, really, and see when it's positive versus when it's negative. So looking at these ones, you can do this in whatever order you want. There's a lot of people who like to work columns. There's a lot of people who like to work rows. It genuinely does not matter how you do it. Just filling it in. I have a tendency to work columns. That's the way my brain likes to go. So if I think of a number smaller than -2, further out this direction, would this chunk be positive or negative? Negative. So like something like -3 or -4 would be ones to like keep in our mind here. So if x is -4, this chunk is definitely negative. If x is -4, would this chunk be negative or positive? If it's anything smaller than -2. For x minus 5. It's going to be negative. -4 minus 5 is going to be -9. That is even more negative. If I have a number smaller than -2, is this chunk going to be positive or negative? Negative. So our function is made up of a negative piece times a negative piece times a negative piece. If I do negative times a negative times a negative, are we positive or negative? Negative. So my whole function is going to be below my x-axis over here. That's what this is telling us. This is telling us that in this zone, from -2 out, we are below the x-axis. We're going to do the same thing, just between. So now we're thinking about between -2 and 0. So in this zone. So something that we could keep in mind would be like -1. Do -1/2 if you're really feeling it, or -3/2. But -1 also works. So is this chunk going to be positive or negative? Negative. Is this chunk going to be positive or negative? Negative. Is this chunk going to be positive or negative? Positive. So is our function going to be positive or negative? Positive. Because we have a negative times a negative, that's positive, times a positive. So it's positive. So let's fill in more. So now we're thinking between 0 and 5. If you want to think a specific number, you absolutely can. Pick something in between 0 and 5. 1, 2, 3, 4. Any of those would work. You don't have to think a specific number. Totally valid. But anything in here, will this chunk be positive or negative? Positive. Will this chunk be positive or negative? That one's still negative. How about this one? Positive. So my whole function, positive or negative? Because we have a positive times a negative times a positive. So we have a negative. One last section to go on this one. Woohoo! So then we're thinking numbers bigger than 5. Bigger than 5. Positive or negative? Positive. Positive or negative? Positive. This one? Positive. So our whole function, positive. We have positive times positive times positive. What this is telling me is this is telling me where my f of x is less than 0 is on these two intervals. Where my f of x is greater than 0 is on these two intervals. That's telling me where it's below and above my x-axis. So when we have our function being negative, that means I know from -2 for forever we are below the x-axis. Between -2 and 0, I need positive y values. I need to be above the x-axis. So it's going to be up here somewhere. That is not a good shape. There we go. It's okay if things have kind of funky bends on them. Totally fine. Between 0 and 5, again, I have a negative piece, so it's going to be below my x-axis. So it's going to be in between over here. Between 0 and 5. And then, since we have our plus down here, our 5 out to forever, we are above the x-axis. And yes, I know that we can logic our way to that sketch and get a really good value there. This is how we can prove it. These negative intervals are where it's below our x-axis. These positive intervals are where it is above our axis. So we find our roots, we find our zeros, we find our end behavior, and we figure out where it's above or below. There's at least one problem on the homework where they give you the positivity table, essentially. Okay. Questions on this one? We're going to look at one more equation today, and then we'll do a little bit more tomorrow, bless you. Because there's one on the homework that there's a hard way and an easy way to do it. This isn't the exact one from the homework, but it's one very, very similar. So it's the same kind of question, but it's a little fractiony and kind of icky. So it's the same instructions. We just kind of want to find out for this -1/9 x cubed minus 3 what the heck is going on. So we'll start this one out the exact same way. We can find our degree, we can find our leading coefficient, all that jazz. What is our degree? 3. What is our leading coefficient? -1/9. So I know I can get my end behavior from that. I have an odd degree and a negative leading coefficient. So we know our end behavior. I know that as x approaches positive infinity, my y's are going to have that same sign as our leading coefficient. So they are going to approach our negative infinity. So my right arrow is going to point down. Since we know we have an odd function here, as x approaches negative infinity, what are our y's going to approach? Positive. The problem for us comes in when we try and find roots. Because, ew, is that gross. Whenever we have a leading coefficient that is a fraction, and we're trying to factor, divide that sucker out. I don't want him involved in factoring. We will be rid of the fraction in the factoring. Ew. So what we're going to do in order to find our roots is I want to take that -1/9 out as a GCF from everybody. If I take my -1/9 and I divide it out of my -1/9 x cubed, we're just going to be left with our x cubed. If I try and divide out -1/9 from -3, so -3 divided by -1/9. Those two negatives are going to wind up canceling out. Think 3 divided by 1 divided by 9. Those two divisions wind up doing a keep, change, flip situation. 3 times 9. 27. So when we have a fraction as our leading coefficient, especially if we need to factor, divide it out, you will get a much better number. A much better number. Because can I factor that? Can. What do we need to remember to use? Soap, because that's nasty. We got to clean that up. That's filthy. When in doubt, we got to use soap, make it cleaner. Gross. So our negative 1/9 is going to sit out front. When we're factoring this, if it helps, think of this being as our x cubed and our 3 cubed. So our pattern is going to be our x with that same sign. Then we're going to have our x squared, opposite sign, a times b, x times 3, or 3x, always plus 9, 3 squared. Now we can get our zeros, our roots. Where are we going to have a root on this one? One of them is real easy to spot. Negative 3. Does this factor more? No. There's not any number that's going to, or any pair of numbers that multiplies by 9 and adds to make negative 3. So it definitely doesn't factor. I could put this through the quadratic formula. Will I get a real answer or will I get an imaginary answer? Imaginary. So this only has one real root. This gives us imaginary answers. We don't have the information, or we don't have we don't know how to graph imaginary roots specifically, so we would just have to guess and check, and that is not what we're going to work with. So this will have imaginary roots. So if we know our one actual root, I know my end behavior, and I actually know one more point here because we know our y-intercept. What's our y-intercept? Negative 3. It's our constant. I can get a half-decent sketch even without a positivity table. I could do a positivity table. It would be a very small one. We only have one real root. And I am on the wrong side there. Because our one real root is at negative 3. We also know we have a y-intercept at negative 3. I know my right arrow is going to point down. My left arrow is going to point up. That is the extent of the information we have. I know that the only place we're going to cross the x-axis is in negative 3. We might have more wiggle squiggles. I need to hit that y-intercept, and I need to make sure we go down. No extra x-intercepts. No loop-de-loops. That absolutely would count as a decent sketch. It's not a great sketch because I'm bad at drawing. You could do this in any number of ways. You might bring this up here and bring it down like that. That's another valid sketch. We might have a wiggle squiggle up here. There's lots of different ways this can be sketched. We don't have the details to get any closer than that. Tomorrow we'll do a couple more problems from section 4.1. So here's the homework problems for 4.1. We are going to keep working with it tomorrow. There's one other kind of question that we haven't really seen, like number 37. We'll talk about one like that tomorrow. But you guys could do a good chunk of it, but we'll practice it again tomorrow. Okay?